Now we are going to build on our previous video where we built a VXLAN network using flood and learn, and we're going to add a control plane to it, some smarts to it, so that way the goal will be to eliminate some of that flooding, because right now it works, but the network has to learn about hosts when it floods them out. So let's look at our diagram, and we'll recap what we did last time, and then we'll build BGP control plane on top of that. So last video we focused on PCs 1 and 3. So just as a summary, I'm gonna do 2 and 4 right now. Test the reachability, then we'll move on to BGP. So I think the first thing I want to do is configure. Let's go to our wiring diagram, and let's configure Nexus 3, this port E14 in VLAN 20. And spanning tree port type edge and no shut. Take this same configuration and put it on Nexus 4. Okay, so now I want to power on. Actually, I'm going to start some captures. So I'm starting to capture on E11 and on E12. And then we will see what happens as these, here we go, E11, E12. And I'm going to power on PC2. What we should see is it'll do an ARP when it powers on. That ARP will go to Nexus 3. Nexus 3, won't really know what to do with it, so it's going to send it to 1 or 2, which is the multicast root of the tree, and then it will send it down to 4. Okay, so I'm going to power on PC2. Okay, it's doing its ARP. Okay, so what should have happened is, PC2 sends an ARP, encapsulates it to Nexus 4. Nexus 4 should have got it. So let's look at the MAC address table of 4. So it looks like it did get it. 68OA should be PC2. 68OA. So that's good. So Nexus 3 flooded it over the multicast tree. It got to 4, and 4 learned it, and it populated this entry. And it did that via flood and learn. Now the same thing should happen in reverse if I turn PC4 on. So let me turn PC4 on right now. Okay, it's doing its ARP. Now let me go to Nexus 3. Let's look at this MAC address. It's 68OC. So now let me go to Nexus 3. Show MAC address, and there is 68OC, and it knows where it's at. So any subsequent traffic, so if I ping between 2 and 4, it'll be unicast. Okay, so there's the pings that are working, and here's the request. So if we look at from 3 to 4, and let's look at the reply from 4 to 3. That gets swapped, but notice it's unicast. If we were to go to this broadcast, maybe this was when the computer turned on, it didn't know where to send it, so it did the multicast. And here's the response. Oh, that's not the right thing. Oh, it got away from me. The response was a unicast, and now every subsequent packet between those two are going to be unicast because the switches know where the host is at. So that's where we're at now with the flood and learn. So what we want to do now, though, is add BGP, which is a control plane protocol, which is going to help eliminate some of this flooding that it's doing. So right now, when Nexus 3 doesn't know where something is at, it floods it. Well, we're going to add some smarts to it, to where the idea here is going to be when, say, PC1 gets turned on, computers usually generate some kind of traffic, anything to populate the MAC address table. Once Nexus 3 learns about the MAC address table, it will take that and send a BGP update saying hey, I've got, this host. It'll send that update to Nexus 1 and Nexus 2, and they will reflect it down to 4 and 5. Now 4 and 5 know where PC 1 is before any flooding even happens. And so we're trying to reduce the flooding here. Now how we're going to do that is we're going to build BGP sessions, iBGP, in this case, between 1 and 3, 1 and 4, 1 and 5, and then between 2 and 3, 2 and 4, 2 and 5. So here we kind of have not a full mesh of peerings exactly, but we're going to use Nexus 1 and Nexus 2 as a BGP route reflector. So that way we don't have to have like a complete full mesh, but we do want redundancy. Nexus 1 and Nexus 2 are going to kind of have the same information because 3 is going to peer with 1 and 2. Now we're going to peer on our loopbacks, so add another use case for why we need those loopbacks and why we need them in OSPF. We're going to peer BGP over these loopbacks. So BGP is going to have the TCP session that's going to be routing from 151.3.3 to 1.1. We're going to establish the BGP adjacency, and then we're going to advertise a certain type of routes over that peering. So let's look at kind of a workflow of like what we're trying to accomplish at the end of the day and how this works. So the first thing that will happen is the computer will turn on. And then when it turns on, again, it generates something. It doesn't really, I'm just going to use ARP in this example, but the ARP is going to be sent to Nexus 3. It's going to learn the MAC address. As soon as it learns the MAC address, it creates a BGP update about that MAC address. It sends it to Nexus 1, which in turn Nexus 1 reflects it down to 4 and 5. So now Nexus 1, 4, and 5 know where PC1 is before PC1 even tries to send traffic into the network. Now at the same time that Nexus 3 sends an update to 1, it sends it to 2 as well. And then 2 reflects that down to 4 and 5. So now we have Nexus 4 and 5 getting two updates of how to get to PC1. And again, all this is before PC1 even tries to send network traffic into the network. So this is kind of set up before it's being used. If it's set up before it's being used via this control plane method, then whenever we start to send traffic, we don't have to flood it. We already know where it's at. So this is like kind of a preemptive way to populate these switches, Nexus 3, 4, and 5, of where the devices are before we actually need that. Then when we need it, we have it. We don't have to flood it. It's more efficient. So that's kind of the idea of what we're trying to accomplish. So if we look at how to configure it, let's start with the BGP sessions. I guess we should start by on the leaves here. Let's enable some features that we need to even unlock some of this syntax. And some of this is just from the documentation. It's just the bunch of features you have to enable to get this thing working. Interface VLAN. We'll actually use this feature later, but it's in the configuration guide now, so I'm just doing it now. It's mostly these, and I'm going to put these on the leaf switches here, which is 3, 4, and 5. All right, and now on Nexus 1 and 2, we only need one thing. We just need to unlock the syntax for something here. So it's going to be NV overlay EVPN. Oh, man. All right. So now we have some of the syntax unlocked. We want to go to the NVE interfaces on 3, 4, and 5. So remember what that was. That's where this is our logical interface that does the encap and decap. That's sourced from loopback 0, and we have all the VNIs mapped to the multicast group. So what we want to do is we want to tell this interface to use BGP first, to try to use BGP, and then if it doesn't work for some reason, then fall back to flooding. So we're kind of making BGP a priority here. This is host reachability protocol, BGP. So that needs to be done everywhere we have like a NVE interface, which is only 3, 4, and 5. So now we've instructed the logical interface to try to use BGP. Now we want to build the BGP sessions here. And there's a decent amount of configuration, but it's templatable. So what I'm going to do is build the session on 3. So 3 is going to have a session to Nexus 1 and Nexus 2. I'm going to build it on 3, and then I'm just going to copy and paste it into 4 and 5 because the configuration is exactly the same. So on 3, like before, we've got to enable the feature before some of the syntax will get there. And I'm going to use BGP 65001, just kind of in the private space for BGP. And then I'm going to point this to neighbor 150.1.1, so the Nexus 1. And then what remote AS is it in? 60, that's the same, so that means it's an iBGP neighbor. Update loopback 0. Again, we're using that loopback again. And we want to turn on or activate an address family, L2 VPN, EVPN. Now this is different than IPv4, where normally you would use BGP to maybe route IPv4 packets across the internet. This use case, we are using the address family L2 VPN to route sort of inside this tunneled fabric that we're making, and we'll see more about this. But under the address family, we need to send community. We need to make sure extended communities are enabled, because that'll be used to carry some values that we'll look at later. So that's neighbor 1. Now we want the same thing for 151.2.2. So this is going to point Nexus 3 to 7K2, but we pretty much want these same values. It's going to look identical. And then send community extended. So let's look at our full BGP configuration. Okay, so we have it on, and then we're pointing one neighbor to Nexus 1 and the other to Nexus 2. So I'm going to take this whole thing, paste it here for 4 and 5. All right, and the last step here will be to do the spines, Nexus 1 and 2. We need to do the configuration back to the leaf switches. So I'm going to configure this all on 1 and just copy it to 2, because it's exactly the same. Now all this is under BGP 65001. All this is iBGP relations. Neighbor, just pointing this one to 3. Send communities extended. Now this is going to have one difference from the leafs, which is going to be route reflector client. Now what this does is iBGP loop prevention rules say you can't pass a route on to somebody else once you learn it. So to get around this, you can just peer everybody to a route reflector and then lax that rule on the route reflector. So this is a BGP configuration, not really a VXLAN configuration. This is a scaling technique with BGP, but we want it on because we want Nexus 3 to send something to 1 and then 1 to send something to 4 or 5. And without route reflector client, Nexus 1 would never pass it on. Now we want this neighbor 151.4.4 to be the same here. And the last neighbor is 5. Okay, let's look at this whole configuration. So we have Nexus 1 pointing to 3, 4, and 5. Now let's put all this on Nexus 2. Grab that feature. Okay, now let's check some of these neighborships and make sure they're up. So show BGP, L2 VPN, EVPN summary. That's the new syntax. So it looks like they're up, and we're even receiving some routes here. I mean, it's just going to kind of run this. Okay, those are all up, receiving routes. Up, receiving routes. Up and receiving routes. Okay. Now you'll notice the syntax is weird, kind of, but it has to do with the multi-protocol BGP. So that's the address family. That's the sub-address family. So if I took away the summary, it would just show me the routes. Now you'll notice that looks a lot different than an IPv4 route. That's route type 2. It's telling you that the next field is 48 bits, which is the MAC address. That's blanked out right now because we're just doing layer 2. So let's look at maybe Nexus 3. Show MAC address so it knows about the host over on 4. Let's look at its table. And it also received the BGP update about 68.0C. 68.0C. So it knows where to send it. And it looks like it may have 2 ways to get there. It's picking one as best. We might be able to see a little more detail if we were to look at this update. Okay. 68 OC. No label next hop. This one's the best path. So the next hop is 151.4.4. So here we turn to the extended community on so it could carry the route target, which is the autonomous system number plus that VNI that we configured. So the route target, we'll talk more about the route distinguisher and route target probably in the next video, but this was the route target is going to tell the switch to import or export certain prefixes into a certain customer's table. And then a route distinguisher is going to be something that helps keep all the routes unique. Get into more of that later. But the basic idea now here is we should be able to eliminate flooding. Let's see if we can maybe prove some of that. I'm going to shut down computers 1 and 3. And then we're going to turn them on and see what happens. All right, we should not see flooding is what should happen. Okay, so 1 and 3 are off. So what I want to do is look at 3. Show MAC address table. So it doesn't know about there's nothing on E13. So as soon as I turn the computer back on, it'll learn about E13, and then it should create a BGP update. That's what we want to see. So I'm going to turn it on. I'm going to turn on PC 1 right now. Yep. And start. Okay, so it did an ARP, which made it to Nexus 3, and that should have created a BGP update in one of these. Let's see if we can. Here's an update packet. Update message. Let me see if I can look at this. So it's from 3 to 1, which is where the BGP session is built. Here's the update message. And here's the extended communities, which we enabled. There's that route target. There's the autonomous system number. More about that later. And local preference, AS path, empty origin, IGP. Here's the actual route. Should be, there's the next hop. NLRI, EVPN, NLRI. Here's the route. Here's some of that detail we were able to see here. So here's the MAC address, 6809. This is kind of the route here that it's sending. So it's taking this information. It learned about that MAC address, and then it stuck it in this BGP update packet, and it sent it to Nexus 1. Nexus 1 sent it down to 4 and 5. 4 should have installed it in its table here. And what the MAC address of PC1 was 6809. And here it is. It's showing up in the routing table here. And so now it's in BGP. Now, Nexus 4, it knows how to get there. And there it is in the MAC address table as well. And so we haven't sent any packets into the network yet. I mean, I guess maybe when I turn PC on, it sent something, some kind of ARP to check for a duplicate IP. But other than that, there's been no traffic going on. So when PC1 tries to ping 20, which I don't even have that on, let me turn PC3 on. Okay. Yep, it pings and it should just be all unicast. So I mean, that's what I wanted to show, is how the control plane can preemptively populate Nexus 3, 4, and 5. So that way, 4, it can know where 1's at before anything even tries to talk to it. That way, when PC3, say it needs to talk to PC1, it sends packets into Nexus 4, it does the lookup, and it finds it. It doesn't have to flood it. And so that's the advantage of using the BGP. So just as a quick wrap up for this video, this is the kind of the workflow. It's powered on, an ARP gets sent, Nexus 3 gets it and creates out of it BGP update, which gets sent down to 4 and 5, and then that's enough to populate their MAC address tables here, or their I should say BGP. Their BGP tables here that tell it, the next hop, where to send it when something is destined to that MAC address location. In this case, we're just doing bridging all layer 2. We'll do routing, add some routing in the next video. That's where some of it gets more configuration, it gets more complicated, more concepts. But when BGP doesn't work or it fails to work, so for example, if PC1 were to come online and it doesn't generate any traffic, so we call that a silent host. So in other words, Nexus 3 may not even learn about the MAC address, even though this port is up in a forwarding state. In that case, when PC3 tries to talk to PC1, it goes to 4. 4 doesn't know where it's at because 3 doesn't even know where it's at. And so in that case, it does fall back to the flood and learn. So Nexus 4 would wrap it up in VXLAN multicast packet, send it to 1, which would send it down to 3, which would send it out that port. Then once he got it, he would respond. Then Nexus 3 would learn about it. But that's the issue, is these silent hosts, which I don't know how prevalent they are, but if they get turned on and they don't talk, then flooding has to happen in order to initially learn about this. But in most cases, the computers, they turn on, they spit out traffic, that'll get turned into a BGP update and distributed, and now we have the control plane all set up before we even need to use it. And for an efficiency technique, I'll just show you. If we go to Nexus 5, it doesn't have any VLANs on it because it's going to be used for another purpose. So it doesn't really install anything. So if this doesn't have the VLAN configured on it, it is getting the BGP updates, but it's not really doing anything with them, because the issue is going to be, like, if it were to install everything, it's more of a issue at the TCAM tables rather than at the BGP table. Yeah, so when it gets the routes, it knows it doesn't have anything to really do with them. Let me make sure it's up. And so it just gets rid of them. It doesn't really use them. So as an efficiency, if it doesn't have a VLAN configured where it knows it doesn't need them, it just doesn't install them. So that's the efficiency of this. So that should be a good example of how BGP is used to set up the control plane before traffic needs to be sent. That way, when it's sent, it knows what to do with it.